So there's a little you can do, although it's perfect private. So what we propose is something called the fit probe rate. This is a better name. It's hard to pronounce. So basically here we want to use some probabilistic distribution to generate this inter-message intervals instead of constant rate. So in this way, we may provide some opportunity to reduce the transmission latency for the real message, because due to the statistical nature, probabilistic nature of this distribution, right? So some of this interval will be larger, some of the interval will be smaller. So now if you transmit this real event message, use this small interval. So then attacker point of view, attacker may not be able to notice this is if it's real or not. Right? It's a very simple idea. But the thing is, how do you really do that? So in this way, we can provide something called a statistically strong event unobservability. So what is this term means? So we give something more formal definition here. We call the alpha epsilon unobservability. So it's a kind of statistically strong event unobservability in which a distribution. So given this distribution of this so this distribution is statistically is indistinguishable from a probabilistic distribution. So which means you have two distributions. Use statistical testing. You cannot differentiate one from another. So if you do, so we will introduce some of the testing methods. See, if they are like a exponential distribution. So in this case, you will see so this is the sample, right? This is the population. So they have both have this the same, supposedly they have the same distribution with the same mean. Right? So this is the CDF. The CDF of this distribution, and this is the CDF of this population distribution. So basically here you measure the difference between the CDF. Right? If they are very close, then it means that they are the same distribution. The same curve in the PDF. And the second part is to measure this the parameter. So parameter here is if we use for example exponential distribution for one, and another is also exponential distribution. Their curve may be the same, but their mean could be different. Right? So you want to also make sure, in this case, not only the shape of this PDF is the same, similar. You also want to make sure this mean is also similar. So there's two parts we should control. So in our example here, we use so in this case we use exponential distribution. So basically it says, okay, this mean, the one parameter is very close in this range, in small range of this in the real one, and we use two parameters alpha to control this goodness of fit of the test to this specific distribution, and we use epsilon to control this closeness of this this parameter to this from the data of the population. Okay, now once we have this concept about this statistically strong event unobservability, so now let's talk about how do we generate dummy traffic. So as I mentioned, you will want to use this probabilistic distribution to generate these time intervals for this event and the dummy or in the real. So in this way, you can in this way we assume this seed of this distribution. This random number generator is a secret, which means that every sensor has a seed to generate these intervals. So we use the exponential distribution because of these properties. One is the exponential distribution has this maximum entropy distribution among all these continuous distribution with the same mean. The second reason is because exponential distribution only has one parameter, because the mean and the variance is the standard deviation, is the same. So in this way, you only need to control one parameter, because otherwise, if you use a normal distribution, so then you have to make sure this mean and also the variance, they are not, both of them are very close to the data of the population, right? So you have more things to control in our case here, we only need to control one parameter. We only need to test one parameter. So that's one of the reasons we choose exponential distribution to generate this time interval. Okay, so now if you use this distribution to generate this bogus message, but sometimes when this real event also happens, you need to transmit them as well. Right? So in this case, what should be our policy? So the policy, we have this two considerations. The first one is the next time interval to transmit and the earlier ones follow the same exponential distribution, which means when you determine the next time interval for the real event, after you add this interval to the original this time interval sequence, it's still exponential distribution, right? Because otherwise the attacker will know, right, this distribution has been changed. Then it can say, okay, there's a real event. And the second goal is we want to make this waiting time to distribute this next this message, which is in this case is the real event, as small as possible, because that's our goal, right? You want to reduce the delay for transmitting the real event. So now the question is, how do we determine this waiting time? So we assume here attacker will perform statistical test to determine if this distribution is still exponential, and also to say if this mean is the same or similar to the one it is supposed to be. Right? Here we assume attacker knows we use exponential distribution. Attacker also knows the mean. The only thing is unknown to attacker is the seed of this random number generator. So what we will do is whenever you generate the next time interval, the value, we will first, the sensor will first do some test. Here we use the Anderson-Darling test to test, see, after I add this value into this sequence, is this still exponential distribution? So in this case, you can start from a small value. Right? You will try it. See, if I add this small value to this sequence, if it's not, if it's much different from this original, the supposed distribution, then you will choose another one. So basically you can add do this iteration, right? You increase this step, so until you find the one which can meet this goal. So in this way, we will make sure if attacker will do the test, then they will still not be able to see this. And another issue is once you give this preference to this real event, so now the interval is become smaller, and you cannot do that every time, right? Because if you always do that, then this distribution will be skewed. Right? So you need to do recovery. So once you send this real event, so later on, the next time you will generate maybe a dummy traffic, so then you have to increase that interval. So in this case, you can make this the overall this mean will be still back to the original one. So we have to use this kind of sample mean recovery algorithm. So basically, in this case, we totally have 4 algorithms to control these numbers. So here is a running example. So suppose in the time point A, the sensor generates dummy traffic, and then the next one is in time B, and the next time is time E. So that's the planned one. But here, during this after time B, at the time C, that the real event occurred. Right, so in this case, you want to find what is the next time you should deliver this message. So if you still follow this original plan, like you send this message at time E, then you don't get anything, right? You don't gain anything. But the good thing is here, we can actually find another value, which is in many cases you can find a value D here is small, very small. So here the CD is the delay for the real event. And from an attacker point of view, now when you observe this sequence, you will still say this is an exponential distribution. And of course, after you send this message, then you have to recover it, because if otherwise it will be, the mean will become smaller and smaller. So in this case, next time you will schedule another point at F. So this is a little bit bigger. So in this way, the mean will be recovered. And from attacker point of view, attacker we will not see this C, right? We assume